Hello, my dear student. Welcome to EPG Pathshala. I am Anchal Srivastava from Department of Physics, Institute of Science, Banaras Hindu University. Today, we are going to talk on module Synthesis of aligned carbon nanotube using spray pyrolysis and arc discharge technique under the paper Nanoscience and Technology 2. After completing this module, my dear student, you are able to learn the following points. After studying this module, you shall be able to learn the synthesis of carbon nanotube using spray pyrolysis technique and arc discharge method. You shall able to learn the growth mechanism of carbon nanotube. You will know about the effect of electric field on the growth of aligned carbon nanotube. As you know, carbon nanotube, which is known as CNT, are allotropes of carbon with a nanostructure that can have a length to diameter ratio greater than 10 to the power 7 of order. These cylindrical carbon molecules have novel properties that makes them potentially useful in many applications in nanotechnology. Formerly derived from the graphene sheet, they exhibit unusual mechanical properties such as high toughness and high elastic moduli. Referring to their electronic structure, they exhibit semiconductor as well as metallic behavior and thus cover the full range of the properties important for technology. Nanotubes are categorized as single-valve nanotube and multi-valve nanotube. Techniques have been developed to produce nanotube in sizable quantities, including arc discharge, laser ablation, chemical vapor deposition, silane solution method, and flame synthesis method. The properties and characteristics of CNT are still being researched heavily, and scientists have barely begun to tap the potential of these structures. Without doubt, carbon nanotube represents a material that offers great potential, bringing with it the possibility of breakthrough in new generation of devices, electrical equipment and biofield. I want to discuss the synthesis of carbon nanotube using a new technique, the spray pyrolysis technique. In this technique, we report the fabrication of freestanding monolithic uniform macroscopic hollow cylinders having radially aligned carbon nanotube walls with diameters and length up to several centimeters. Production of the macro architecture of aligned nanotube for use in filtration application. Here I want to discuss the synthesis setup, which is spray pyrolysis setup. In this setup, it consists of a nozzle attached to the ferrocene benzene solution supply used for releasing the solution into a quartz tube mounted inside a temperature controlled cylindrical furnace. By using a continuous spray pyrolysis method, we have synthesized macro scale hollow carbon cylinder up to centimeter in diameter and several centimeters long, with wall ranging from 300 micrometer to 500 micrometer thick, consisting of micrometer length aligned multi-wall carbon nanotube. The aligned nanotube that forms uniform nanoporous cylindrical membrane walls are synthesized from sprayed ferrocene derived iron catalyst. The nanotube grown in radial direction on the wall of removable silica tube template, leading to formation of freestanding and continuous hollow cylinder carbon tube. This provides a monolithic nanotube macrotube formation. Benzene ferrocene solution was injected into the quartz tube using argon as a carrier gas. The temperature of the furnace was raised up to 900 degrees Celsius. The formation of CNT microstructure was strongly dependent on the nozzle size and flow rate of solution. The removal of the assembled bulk nanotube column was done carefully in infiltration of acid along the inner wall of quartz tube. Now I want to discuss the structural characterization of as synthesized tube made up of carbon nanotube. The first photograph of bulk tube is shown, where it is showing that the tube which is made up of carbon nanotube is of the order of 5 millimeter. Aligned tube with radial symmetry resulting it in a hollow cylindrical structure. Detailed structural characterization of CNT microtube is shown here. A broken piece from 300 micrometer thick microtube wall consisting of well-aligned MWCNT bundles is shown. The length of the MWCNT corresponds to the wall thickness of the bulk structure. Figure B shows the dense packing of this aligned structure. An scanning electron microscope image of a thin section extracted from the membrane is shown in C. Figure D and E are the transmission electron micrograph images of the tube forming these macrostructures. These are well graphitized wall of MWCNT. The range of inner and outer diameter of these nanotubes were found to be 10 to 12 nanometer and 20 to 40 nanometer respectively from TEM analysis. The factor which affects the CNT growth. As I told that the flow rate of the carrier gas, which is argon in our case, plays a very important role. The optimum result was obtained for argon flow of 4 and 5 liter per minute, and under these conditions the CNT diameter were between 70 and 110 nanometer. Meanwhile, the CNT growth rate was about 1 micrometer per minute. For argon flow of 3 liter per minute, only carbon iron nano microspheres of diameter below 0.5 micrometer is formed. When flow was about 5 liter per minute, the diameter of CNT was smaller and ranges from 20 to 50 nanometer, and the length decreases about the half. Let us discuss the effect of ferrocene concentration. Here we can see in the figure that the length of CNT is directly related to the feeding time of ferrocene toluene to the reaction chamber at proper condition. the optimum condition has been seen that the concentration of ferrocene is 20 gram per liter in this case. Let us discuss the arc discharge synthesis of carbon nanotube. The carbon nanotube were produced by direct current DC arc discharge in helium ambient at a pressure of 500 torr. Two graphite rods, which is visible in the figure. The positive electrode is of the order of 7 cm length and 0.7 cm breadth and 0.7 cm height, and the negative electrode is 5 cm length and 0.54 cm diameter were used as electrodes for arcing. The voltages and the current used for arcing were 20 to 30 volts and 200 ampere respectively. The electric field is applied after the arc has run for 3 minutes. The field gets applied by sorting the electrodes, after which the arcing ceases. That is shown in figure clearly. So, one of the most important factor which affects the CNT growth is the flow rate of the carrier gas. Now I want to discuss, in which I discuss the effect of electric field on the CNT growth. This depends on the arc discharge method, where I have already discussed in my previous module the growth of CNT. But how one can grow the aligned CNT with applying electric field will be discussed here in this case. In order to find out the possible alignment effect for tube due to electric field, the microstructure details of the tube was investigated, employing the technique known as transmission electron microscopy. As one can see, when no voltage is applied, the tube gets formed with a random dispersion shown in figure. If we apply a voltage of 4 volt on the tip of the two electrodes of graphite, the partial alignment has been taken place. The microstructure detail of the tube formed in the presence of electric field suggests the commencement of the tube alignment. For the field corresponding to 6 volt, the optimum alignment of the tube takes place. In this case, the tubes are aligned to a very high degree and clustering in the form of bundle. In order to confirm the reproducibility of the alignment of carbon nanotubes, transmission electron microscopy exploration were carried out from several regions of the tip of carbon electrode, produced by specific voltages. It was observed that the alignment of CNTs for electric field corresponding to 6 volt is not off by more than few degrees. For lower and higher field, the alignment of tube is only partial. For higher field, voltage greater than 6 volt, the tip region start getting heated up to as evident by a red glow appearing near the cathode region. This heating effect would disturb the alignment of tube. For lower field, less than 6 volt, the electrical field would not be strong enough to cause alignment effect. The variation of geometrical parameters and orientation of tubes with respect to external electric field has been discussed. One can see that external electric field applied in volt is written in the left side, and next to that the state of alignment has been mentioned. Dimension of the tube in terms of their length, and average diameter has also been shown. If there is no electric field applied, means 0 volt, in that case the state of alignment is highly random and the length is around 2.5 micrometer and diameter is around 20 nanometer. When I will talk about 6 volt, the state of alignment is really aligned, forming bundles. The average length increases up to 12 micrometer and diameter up to 60 nanometer. Whereas below 6 and above 6, their state of alignment either random or partially aligned, and average length is lower than the 6 volt, as well as the average diameter is also lower than 6 volt. I want to discuss the mechanism behind the alignment of CNT in presence of external electric field. The random orientation of carbon nanotube in the absence of electric field is shown in figure. When an application of electric field has been shown by the horizontal line with arrow, which induce the shifting of charge density towards the positive polarity on the surface of the tube. The distribution of charge on the tube surface provide an induced dipole moment resulting in a torque. Torque is equal to P cross E, where P is the polarization and E is the electric field. The torque aligns the tube in the direction of field. The dark and light shadow depicts the higher and lower charge density in the picture. In last picture, the tubes are fully aligned in presence of external field. Charge distribution is still there due to the field, but the torque is 0 because P cross E and sine 0 is 0. P cross E is P dot E sine theta, and theta is equal to 0. Therefore, there is no torque is applied. Shows the well-aligned tube after removal of external electric field. I want to discuss the pattern growth of carbon nanotube obtained by high density plasma chemical vapor deposition, which is HDP-CVD. The carbon nanotubes were obtained by high density plasma chemical vapor deposition system that uses a new concept of plasma generation. In this case, a planar coil coupled to an RF system for plasma generation and an electrostatic shield for plasma densification are used. In this mode, high density plasma are obtained. For the ion acceleration, another RF system in planar configuration is used, which is shown in the figure. The substrate temperature was not controlled but measured by a type K thermocouple, which indicated that the temperature never exceeds 90 degrees. For the CNT growth, the pure methane plasma processes were used. The HDP-CVD system has a main chamber with a diameter of around 35 cm, where the electrostatic shield with diameter of around 30 cm is localized. The electrostatic shield can be heated up to 600 degrees Celsius by the infrared heater. The planar coil has been put in the upper part of the chamber over a borosilicate window and is covered with an electrode shield. RF power of around 13.56 MHz is applied to the planar coil center and also at the lower electrode. The vacuum system is formed by a turbomolecular pump with a nominal outflow of 400 liters per second, and an auxiliary mechanical pump. The minimum basis pressure that the system can reach is 2.1 into 10 power minus 7 torr. In HDP-CVD system, there are two gas distributors. The main distributor was constructed in the cover of the chamber, where a small homogenizer chamber, secondary distributor of the gas, exists. The distribution of the gas in the process chamber has been made by a hold ring. The HDP-CVD system has been created to work with gases with 6 different types and liquid with 2 different types at the same time. Thus, it is possible to obtain DLC film with additive nitrogen, fluorine, oxygen, etc. The substrate used to obtain the CNT were 3 inches diameter silicon vapor, 380 micrometer thick and with orientation of 100. They were submitted to Piranha clean followed by a dilute HF dip. Iron precursor material was deposited on the substrate by a magnetron sputtering. The iron layer was defined using optical photolithography and oxygen plasma treatment. These steps were used to pattern the silicon vapor surface before the CNT growth. The CNT were grown after the sample preparation with the parameter of 15 millitorr, 250 watt coil power RF, 13.56 MHz remote plasma, 14 SCM methane, and the deposition time were 3 hours. I want to discuss the application of aligned carbon nanotube. There is a lot of application of aligned carbon nanotube which are listed here. The field emission devices is one, black body absorber, carbon fiber ropes, adhesive films, gas sensor, fuel cell, supercapacitor, battery, etc. I want to discuss very little about some of them. Let us talk first about field emission devices. CNT have high aspect ratio and induce very high local electric field intensity around the tip. Field emission in solid occurs in intense electric field and is strongly dependent on the work function of the emitter material. It has been seen that CNT gives a very intense field emission property. Let us talk about black body absorber. This vertically aligned carbon nanotubes array offer a unique light absorbing surface due to their extremely low index of refraction and the nanoscale surface roughness of the aligned CNT. The next one is carbon fiber ropes. Vertically aligned nanotubes can be processed through volatile solution or twisted to condense into spun CNT yarn or ropes, and this can be used as a rope with a tensile strength of around 1 gigapascal and can be used as a fiber rope. The next one is adhesive film. This vertically aligned nanotubes can be used as additive films and can be work on the principle of gecko feet in this case. Similarly, this can be used as a gas sensor, fuel cell, and battery application. So student, let us now summarize what we have learned in this module. So we have discussed the two different methods. One is spray pyrolysis for growing CNTs and the second one is the discharge technique and application of electric field to get aligned carbon nanotube. This is the two different techniques by which one can grow aligned carbon nanotube. Let us discuss one by one. So the first one, where we did the spray pyrolysis technique. In this technique, a mixture solution of benzene and ferrocene has been used for the synthesis of CNT. We optimize the condition of flow time, the concentration of ferrocene in benzene, and many other parameters, which gives the good growth of aligned carbon nanotube. The effect of argon gas flow rate and the concentration, these are the important parameters and has been discussed for the growth of CNT in this module. Now the second one, which is the discharge technique, has been applied for the synthesis of CNT. We have seen that optimum condition is 6 volt in this case to get good aligned carbon nanotube. However, below that and above that, we are not getting aligned CNT bundles. The alignment of this nanotube has been achieved with the external field of 6 volt in this case. The best alignment has been found at external voltage of 6 volt, where the field is around 1888 volt per centimeter. The distribution of charges on the tube surface provide an induced dipole moment resulting a torque. This torque is nothing but P cross E, where P is the polarization and E is the electric field. The torque aligned the tube in the direction of field. Thank you.